Everyone's space-time is different from everyone else's. No one can exist in space exactly where I am, thus no one can experience time exactly how I do. But your space-time is pretty much exactly like mine, so your experiences are humanly identical. Black holes warp space-time, meaning space-time near them is very much different from space-time near us. In the last video, we saw that this means space behaves very differently than what we expected. Now let's explore what this warpage means for time. Although the distortions in space make it essentially impossible to orbit near a black hole, we can still get very close if we have strong engines and stronger bones. If we simply point our engines towards the singularity, we can resist the sultry curves of the black hole and get closer. This of course means our engines need to output more and more thrust the nearer we get, which means the occupants will experience a greater and greater downward force smushing them into their seats. This is not a pleasant scenario, so we're going to pretend our ship has some sort of anti-gravity device. What happens as we get closer? Orienting ourselves is not the easiest thing. As we descend, the black hole bends more and more light from the horizon down into it. This causes the ever-consuming blackness to bend up around us. As we pass through the photon sphere, the last possible chance for light to arrive directly from the horizon vanishes. Geometrically, we are still outside of the black hole, but to our eyes, it looks like we've now entered inside. The further we go, the more light bends away from us, and our window of the universe above shrinks. This creates a bit of a conundrum. How do we know when we've reached the event horizon? Unlike the ISCO and the photon sphere, there's no tangible boundary we can point at and say, there it is. Down here, everything is as black can be. There's two things we can do to counter this. The first is just simply watching our ever-shrinking window above us. When that shrinks to a point, we are directly above the event horizon. Or we can measure the distance between the ISCO and the photon sphere and divide that by 3. Once we've traveled that distance beyond the photon sphere, we've crossed the event horizon. Our ship has fancy computers and thus uses those distances to calculate and then project a hologram of where the event horizon is for us to see. Finally, we reach our destination. 1.01 Schwarzschild radii from the singularity, just above the event horizon. Our engines thrusting with unimaginable force and our anti-gravity device working overtime to keep us comfortable. Now we can experiment to observe the strange new reality we inhabit. Before descending into the black hole, we left a probe orbiting above at the ISCO. Every time the probe passed overhead, it sent out a radio wave signal at 10 MHz. A light wave's frequency is time dependent. If our time is different down here near the event horizon, we should observe a frequency other than 10 MHz. The equation for time dilation is this, where x is the distance in Schwarzschild radii from the singularity and the reference frame is of someone very far from the black hole. Our orbiting probe is not very far from the black hole, so we need to calculate the time for both of these. We find that at 1.01 Schwarzschild radii, our time is running at 12% the rate of our probe. So for every second that passes here, 8.3 seconds passes for it. When we measure the emitted radio wave frequency, we see that it's jumped to 83 MHz. Time is indeed running slower here relative to those further away. Now the most important question to ask is, but why? For some reason, the universe has decided that physics should behave the exact same way no matter where you are within it. This is the concept of general relativity. No matter your reference frame, light will always travel at the speed of light. Since speed or velocity is a measurement of space and time, then the only way to keep light at the speed of light for every reference frame is to make modifications to space and time. Let's look at the space-time around our black hole. This is an embedding diagram. It's a two-dimensional representation of three-dimensional space. Just like how we in 3 dimensions can't observe the 4th dimension, those living here can't observe the 3rd. So even though in reality objects will be moving along curves, those in this world cannot see them. Without gravity, out here far away from the black hole, objects move through space exactly how we'd imagine them to in 2 dimensions. However, let's see what happens when a photon approaches our black hole. Photons are light and thus must move at a constant velocity. Yet as we watch our photon from the point of view of someone within the universe, the photon appears to start slowing down. Something is wrong here. Although we cannot observe light in this manner, this is conceptually what is happening. The space around the black hole becomes more and more bent into the higher dimension. Thus, part of our photon's journey that we can only observe in the lower dimension is occurring through the unobservable higher dimension. Therefore, time itself slows down in gravity wells in order to allow light to transverse this extra distance. Why must the speed of light always appear the speed of light? I don't know. There's not really a reason except then physics wouldn't work. It's important to remember that for every instance along our light's journey, it appears to be moving at the speed of light for anyone at that frame of reference. If we decided to start here and move away, we would see that the light seems to speed up the further it gets from the black hole. This diagram also shows gravitational acceleration. From the point of view of someone falling into the black hole, they will simply travel in a straight line at constant velocity. But because time starts running slower, they will arrive sooner than they expected. Now you have the philosophical question of, is arriving at a destination sooner than expected different from arriving somewhere at a faster speed? But really, they are two descriptions of the same thing. At the event horizon, gravity appears undefined. That is to say, the slope or tangent of space-time appears completely vertical. That means space or gravity is flowing at the speed of light, and thus all of the light's movement is in the higher dimension, meaning it can't move anywhere in the lower dimension. Thus, time halts. I must stress this is all relative, and appears undefined is the key phrase. Mathematically, the curve looks like this down to infinity. But for our observer, this far out, space is moving at the speed of light here, meaning it appears completely contracted along the direction of motion, and thus it looks completely vertical or undefined. Relativity is weird. The last question we will tackle today is, what does it mean then to interact with the event horizon, or the place where time seems to stand still? Can you really not go past it and come back? What if we stuck a really long pole from our spaceship out past the event horizon and then pulled it back? Surely that would be possible, right? Well, first, it's a ludicrous notion. No materials would be able to maintain integrity that close to and resisting the gravitational acceleration of our black hole. But it doesn't hurt to think about. The first caveat to explore is that we like to think objects are one complete thing, that the two ends of our rods are part of a single entity. So when I move this part of the rod forward, the other end moves simultaneously as well. However, what really happens is that you apply a pressure front of electrons pushing against electrons that travels almost the speed of light through our rod. As we descend our extremely crazy long rod down towards the event horizon, time for the end closest moves slower than for the end we are holding on to. So one of two things is going to happen, and both seem equally valid. The first theory is that the end of the pole at the event horizon perceives time further from it to move ludicrously fast. Thus, as you push the rod towards it, it receives all of those pressure waves from electrons very quickly, and it explodes or breaks apart. But you wouldn't be able to observe this, as the light from the event horizon would be too redshifted to see. The second theory is that compared to the end we are holding on to, time near the event horizon is running ludicrously slow. This creates a very strong pulling force which would snap the rod much like a rope breaking from too much weight. I honestly have no idea and will not guess which is more likely. This does not mean that if you fall into the event horizon you will explode or be ripped apart. This is merely a product of the fact that being motionless near the event horizon and further from it are two completely different states of being, and those two states don't like being connected to one another. Once you let go of the rod, it becomes an inertial reference frame and suddenly everything is fine. This is because, although time is running slower for the part of the rod near the event horizon, the matter has also accelerated and is moving faster than the matter in the rod further from the event horizon. This balances out, and thus our rod falls in as if it was anywhere else in the universe. Thus concludes our in-depth look at the distortions of space-time around a black hole. There are many other things to discuss about these unreal phenomena, the fact that they can have charges or spin, Hawking radiation, and their temperature. Perhaps these are topics to return to another day, but the next question to ask is, why and how do black holes form?